Hey there. So if you've ever written a Python function, passed some data into it, and then been completely baffled by what happens next, you're in exactly the right place. Today, we're going to tackle one of the most classic, confusing, and honestly crucial topics for any Python developer. All right, let's get into it.
So you go looking for an answer, right? And almost immediately, you run into this definition, often quoted from Python's own docs and highlighted in a fantastic article by Robert Heaton. Object references are passed by value. Sounds simple, doesn't it? Yeah, except it's really not. For most of us, this phrase just creates more questions than it answers.
And yeah, Heaton just nails it when he says that if that definition makes you want to punch something, you are definitely not alone. It's a very precise sentence, but it's also deeply unhelpful. It feels like it's hiding the real answer. But don't you worry, we are going to unpack it and actually make it make sense.
And all of this confusion leads us to what I like to call the Python passing paradox. So what is it? Is Python passed by value or is it passed by reference? Because sometimes it acts like one and other times it acts like the complete opposite. What is really going on under the hood? And look, this isn't just a beginner problem. I've seen developers at all levels get tripped up by this. I absolutely love this quote from a learner on Reddit because it just perfectly captures the feeling. I'm confused, and I'm not even sure how or why I'm confused. It's like a universal rite of passage in Python, and today, we're going to get through it together.
Okay, so to solve this paradox, we need to get one single powerful idea burned into our brains. This is the key that unlocks everything else. And that idea is this: names aren't things. In Python, the variables you create, they aren't the data itself. They are just labels that point to the data.
Robert Heaton's article shares this absolutely brilliant analogy from the author Philip K. Dick. Hamlet was not written by Shakespeare. It was merely written by a man named Shakespeare. See what that does? It perfectly separates the label from the person. Shakespeare is just the name. The man is the actual object, the person who did the writing. This is exactly how Python thinks about your data.
So let's be crystal clear about this. A variable in Python, it's just a name. It's a label. Think of it like a Post-it note that we stick on something. The object is the actual thing that's living in your computer's memory. You know, the list, the dictionary, the number. One object can have many names pointing to it, but a name only ever points to one object at a time. This right here is the crucial bit. Okay, so with that core concept in our heads that names are just labels for things, let's do a quick look at the two classic models that other programming languages use. Understanding these is going to make Python's unique approach really stand out.
Right, so in a pass-by-value world, the function gets a complete copy of the data. The best way to think about it is like photocopying a document. Whatever you scribble on that copy, well, it doesn't change the original one back on your desk. But with pass by reference, the function gets a direct link, an alias, to the original variable. This is more like sharing a Google Doc. Any edits you make are seen by everyone immediately.
Let's see how this actually plays out. So in a pass-by-value system, if we have a list, say 0, and we pass it into a function, that function gets its own private copy. Any changes it makes are to that copy, inside its own little bubble. The original list outside, it stays completely untouched, safe and sound.
But now, flip that on its head. In a pass-by-reference world, that exact same action has a totally different result. The function gets a direct line, a portal, to the original list. So if the function modifies that list, boom, the original one changes. The link is direct, so the change is shared.
So, which one is Python? The answer is neither. And that's the big reveal. Python uses a system that's best described as pass by assignment, or if you want to be more formal about it, pass by object reference. And this system right here explains why we see all that confusing behavior.
Let's look at the first piece of evidence. If we create a function that takes a list and simply appends an item to it, the original list outside the function is changed. We're using the name list inside the function to find and modify the object it points to, and since it's the same object the outer variable points to, the change is visible to everyone. This looks exactly like pass by reference, right? But now, look at this. If we have a function that takes that same list, but this time it reassigns the name list to a brand new list, well, the original variable outside is completely unaffected. See, here we're not changing the original object at all. We're just telling the local name list inside the function to peel off and stick to a totally new thing. The original name outside doesn't care, it stays put. This looks exactly like pass by value. This is the paradox.
So how on earth can it be both?
Okay, let's just break down exactly what's happening. These 4 steps, this is the mental model you need. First, when you call a function, Python doesn't copy the object, it copies the reference, the little arrow pointing to the object. Second, you now have 2 names, one outside, one inside, but they are both pointing to the very same object in memory. Third, if you use the name inside the function to change that object, like with .append, that change is visible everywhere. Why? Because there's only one object to change. And fourth, this is the kicker. If you reassign the name inside the function to a whole new object, all you're doing is moving that internal post-it note to a new spot. The original name outside stays right where it was, still pointing to that original object.
Okay, so why does any of this actually matter in the real world? Well, it matters a lot, because misunderstanding this leads directly to one of the most infamous bugs in all of Python, the mutable default argument trap. Come on, if you've used an IDE like PyCharm, you have definitely seen this warning. You know the one. You define a function with a default argument, maybe an empty list or a dictionary, and it gets this little squiggly line under it. That warning is desperately trying to save you from a very, very common pitfall.
And here is that bug in action, straight from a classic Stack Overflow question. We define a function, give it a default dictionary. The first time we call it, everything seems fine. But then the second time we call it, wait, what? It remembers the data from the first call. The dictionary is just accumulating values across totally separate calls. This is almost never what you want to happen.
And now you know exactly why this happens. It goes right back to our core idea, names aren't things. That default dictionary object, the thing itself, is created only one single time when Python first reads and defines the function. Every single call to that function after that gets a new local name, but that name points to that very same dictionary object. So when you modify it in one call, you're actually changing the single object that all future calls are also going to use.
So what's the safe way to do this? Well, the solution is really simple, and it's standard Python practice. Here's what you do. First, set the default value to none. None is immutable, so it's totally safe. Second, inside your function, you just check if the argument is none. And third, if it is, you create a fresh, new, empty dictionary right then and there. This makes sure that every single call gets its own unique object, and you avoid that trap entirely. So that baffling phrase, object references are passed by value, it actually makes sense now, right? You're passing a copy of the reference, a copy of the pointer. And understanding this doesn't just solve some weird puzzle, it gives you a much deeper insight into how Python itself is designed. It kind of makes you wonder, what other profound design choices are hiding right there in plain sight, just waiting for us to understand them?